Okay, so let's talk about induction. Induction means when you take a current, changing current, and you use it to produce another changing current. We did some examples of that in class. Let's suppose you have a case where you have two coils that are wrapped one over the top of the other. And we're going to consider these to be solenoids. So we have coil 1, and then we have coil 2. And we assume that each has a certain number of turns, N1 and N2. They have the same area, that is, that one is wrapped right on top of the other. And they each have the same length. Alright, so what we're going to do is we're going to take these two coils that are wrapped one on top of the other, and we're going to put a switch over here and connect it to a battery so that we can put a current through the first coil. And then we're going to put a voltmeter over here to measure the EMF that's introduced in that second coil. So I should say that this is voltage 2. Alright, we can figure out what voltage 2 is in terms of current 1 by using Faraday's law. And so let's see how that would go. It's going to be something like we throw the switch, that's going to produce current I1, and then current I1 is going to go through coil 1. That's going to produce a B field in that coil. That's going to be producing a flux in coil 2. And in fact, that's, since the current is changing when we close the switch, that's going to give us a d phi to dt, and then through Faraday's law we're going to get an EMF which we will measure with that voltmeter V2. Okay, so that's the general idea. We're going to use a current in the first coil to induce a voltage in the second coil. Alright, I'm going to erase this. Okay, so the V2 is going to be equal to the EMF that's induced in coil 2. That's equal to minus the change in the flux through coil 2 with time. And so we've got a coil that has N2 turns. It's going to have a field through it which is produced by the first coil. And it has a cross-sectional area, so this is equal to minus d dt of the number of turns in the second coil times the area of the second coil times the B field that was produced by the first coil. Okay. The B field produced by the first coil, if we assume that it's a solenoid, is just equal to mu 0 times the number of turns on the first coil divided by the length times the current I1. And so we get that the EMF induced in the second coil is equal to minus d dt of N2 A2 times mu 0 N1 over L times I1. All right. So these are all geometry terms, right? They're not going to change. They just depend upon how the coils were put together. And this I1 is the only thing that's going to be changing in time. So we'll get N2, N1, A2 over L, mu 0 times d I1 dt is equal to this EMF induced in the second coil. All right, so we put a changing current in the first coil. It induces an EMF in the second coil, and all of this just has to do with how the coils were constructed. Remember, we took two long coils. They were right on top of each other. They had the same length and they had the same cross-sectional area. We often use devices like this or setups like this, and this quantity here is called the mutual inductance between coil 1 and 2. Let's see, I left out a minus sign there. There's a minus sign here, and this is di1 dt. So this is the mutual inductance. And if you think a minute, a transformer like you use at a power station or like you use for your power supply on your laptop is a mutual inductor. It takes current in from the wall and it turns it into an EMF that's used to power your laptop computer. The units of this quantity here are measured in henries. That's the metric unit for inductance. Joseph Henry was one of the great early American scientists. He was a professor at Princeton, and he was also the first secretary of the Smithsonian Institution. And he did a lot of researches on electromagnetic circuits and interactions. Okay, so that's mutual inductance. We could have played the same game except producing a voltage inside a coil itself in the following way.